Alright, hi y'all. Today we're going to be going over power computations in ECE 5380 or power electronics. And this is going to be a little bit different than previous videos where, I've done just practice problems. We really have to understand like where we're getting these equations from, especially in power electronics. If you're going to ever pursue a career in some sort of power electronics, yes, you can, just look up the equations yourself, but knowing where these come from is it's pretty important because we have different types of waveforms. We're not dealing with just sinusoids and square waves anymore. We're not dealing with periodic waves sometimes. We're dealing with non-periodic waves and non-linear loads. So this is where you have to get into the very nitty-gritty of analysis of circuits. So if you want to think about this as like circuit theory on a little bit on steroids, that's exactly what this is going to be like. At the very beginning, we're going to be going through power computations, and the most important, not the most important, but the first thing we delve into is average values. Okay, so one thing we have to know about average values is, what is an average value? Well, if you know a sinusoid, we have this, and I'm only going with sinusoids for now. Imagine this was periodic. This is a period t. This is t over 2, 0 here, right? So let's say we take the integral of this sinusoid. Sine of x from 0 to t, 1 over t, right? This is the definition of an average value, right? So what will be the average value of this periodic waveform, this sinusoidal periodic waveform? Well, this is going to be 0 because the area on top matches the area on the bottom, right? So if we split up the integrals here, we split it up from 0 to t over 2 of sine of x plus the integral from t over 2 to t of sine of x. Well, what's the integral from 0 to t over 2? What is this area? Let's say this is 1. It's going to be, let's just say 1, right? There's an area of 1. But then we go to the negative side. This is still negative 1. This is going to be minus 1. It's going to be 0. So a sinusoidal periodic waveform. I guess a sinusoid is a periodic waveform, but just to back up, what I'm saying here is sinusoidal periodic waveform. The average value of it will be 0. And so this becomes a problem because, in the grid, we are sending sinusoidal waveforms. We can't call a sinusoidal waveform an average value of 0. There has to be a better way. Okay, and that's the next step we're going to get into. But for now, we're going to delve a little bit deeper into average values. So what is the definition of an average value? So the average value is going to be equal to the integral of the instantaneous value. So in this case, this is a voltage. We'll call this voltage. The definition of average voltage is the integration of instantaneous voltage from 0 to t, a period, divided by that period. Okay? So you could do the same thing for current. The average current is going to be equal to 1 over period times the integral from over that period of the instantaneous current. Finally, the last one, of course, we all know this is average power. This is the one that we're going to be asked for most of the time because most of the time we're worried about the power. We're not talking about what's the current, what's the voltage. We're usually concerned about how much power is this load absorbing, whether it be nonlinear or linear. So the average power is going to be equal to the integral over a period of instantaneous power divided by that period. This is the definition of average power or average values. But remember before I was talking about sinusoid waves, right? Sinusoidal waves where the average value is 0. There has to be a better way of describing a sinusoid's average, quote unquote, average value. This is where they come up with the idea of the root mean square value, the RMS value. Okay, so instead of taking the average value, what they do is they do this thing called the root mean square, the RMS. And what this is, it's very similar to average value. Instead, we're doing the root mean square. So we do the root of the mean, and the mean is the same thing as average. So you do 1 over t integral over that period of the instantaneous value voltage, and we take the square, and we do is we take the square of the function inside. Okay, so hopefully this made sense of like, well, why are we doing this? For some different waveforms, for example, for a sinusoid, it's going to be the V max, or the amplitude, divided by the square root of 2, equal to the RMS voltage. For a square wave, I could be wrong about this, by the way. Hold on. Let me look this up real quick. And so square wave is going to end up being the RMS voltage is equal to the amplitude here, Vm, times the square root of the duty cycle. And the duty cycle is it's going to be the amount, the upkeep time, divided by the total period. And now, finally, we have, this sort of square wave. Let me get this drawn correctly here. Right, so we have this square wave, or not square wave, triangle wave, or sawtooth wave, however you want to say here. And what this is going to be is it's going to be that V amplitude still, or Vm, divided by the square root of 3. You can think about a triangle or a cone. If we think about volume, we take the root 3 of it. And this is how we're going to get RMS values. This is how they are usually seen instead of the amplitude. And so this makes it much easier for others to communicate what those values actually are. Now you might be thinking, up here I said average values for current and power. Those are working, those are the same. Can we have the same thing as RMS, right? For current you can, so we have the current RMS. And this is going to be the same thing. It's going to be the square root of the mean over the period of the instantaneous current, and of course squared. And another thing is the RMS current, this quote unquote like total RMS, because the RMS or the current can have different harmonics per se. Voltage can also. So you know what? Instead of saying I'm going to say in, or no, not in. We'll say like A. Okay, A RMS, some arbitrary value or variable. What we can do is take the same thing. Oh, not I. Sorry. Of the DC component. This is where we're going to started getting into Fourier series, later in this video, or probably in the next video. But I'm going to show you this equation because this is how you would find the RMS value for some arbitrary variable. Okay, so you have the first harmonic. Then here you have the second harmonic. And when I say harmonic, I mean these are your AC components. This here is your DC component, and sometimes instead of it saying DC outright, it'll have a little not symbol. So you see how this is a 1. Why doesn't it start at 0? Well, it's because the DC component is your 0. This will be your second harmonic, your second component of your AC component, and then it'll keep going on forever until you have no more AC components. And notice these are your RMS values, and they're squared. The DC component is a DC component. That's what it is. Later on, we'll see why that is. It'll make more sense when we do problems, but this is what we have to end up doing, and this is very important, especially when we get into non-linear loads and non-sinusoidal sources. This is very, very important. It comes up so often in this class. All right, so now we've gone through, average power and RMS values, and with these two concepts, you should be able to do some of the practice problems at the back of your textbook. Now what we get through is we get to total power. Something else I have to kind of mention is that instantaneous power is equal to the instantaneous voltage times the instantaneous current. So this is just, a refresher. We have to remember that voltage times current is power. And now we get into, total power. And this is where we get into complex numbers. So if you remember from circuits 2 and electronics, mostly circuits 2 though, and actually circuits and systems as well, we do a lot of, practice and exam problems with complex numbers where we're in the imaginary plane, because we have the inductor and the capacitor. And it's easier to jump into a different plane. Instead of saying in the time domain, we go into the phasor domain. Anyways, here we go into total power. So what is total power? Well, it's defined as total power is equal to the average power, or the real part, P, plus the imaginary part, JQ, or J times the reactive power. So P is real power and Q is reactive or imaginary. Something else to note is the real part is our average power. So if they ask for the total power, or they give you the total power, and you can calculate the average power using these equations up here, that means you can find the reactive power very easily using this equation. So now, again, the real power, P is equal to S cosine of that angle theta. It's also equal to the RMS voltage times the RMS current times cosine of the angle between them. Okay, but what is S? Where did this S come from? Okay, well, S is going to be equal to the square root of your P squared, your average power squared, plus your imaginary power squared, or your reactive power. And this is going to be your apparent power. It's called apparent. So it's the magnitude, essentially the magnitude of your total power. So this becomes very important because you might be asked, how much power can this, this drill deliver, right, to this nail that you're trying to push into this wall? Well, you can calculate the total power, of course, but that includes some reactive or imaginary power. The drill can only consume and deliver real power. So when you solve, and if you're asked this question, then you would have to solve for only real power. So you would only want this, your RMS current and your RMS voltage. Notice theta is equal to the voltage phase angle minus the current phase angle. This is going to be equal, or that's what that is, right? So in problems, you're going to be given, this RMS current as 170, let's say 120 pi t plus, I don't know, 120 degrees, right? It has a phase angle of 120 degrees. So this is your theta v. And let's say your current is, I don't know, 2, it's in the same frequency, but it has a minus phase angle, right? It has a negative phase angle of minus 30 degrees. So now this here is your theta I. So theta will then be 120 minus a negative 30, or 150 degrees. So this is what you're going to be getting. And of course, your VRMS will be this value. If it doesn't say directly, it'll be 170 divided by square root of 2, because it's a sinusoid. And then your RMS current will be 2 over the square root of 2, because again, it's a sinusoid. Oh, oops. 170, we'll say cosine. I forgot about the cosine. Sorry about that. Okay, so that's how you would go about this. VRMS is just the value, IRMS is just the value, and then you have the same frequency, so you can use this real part power. If they have different frequencies, we'll get into that in a different video, but for right now, let's keep everything simple. We're just getting the equations down. So now you have your real part. We've gone through real part. Now we have reactive part, your imaginary part. So Q is going to be equal to the apparent power, S, times sine of theta. So it's the same thing, the RMS voltage times the RMS current times the sine of the angle between them. Same thing, just like the theta's representing the same thing, and we'll be able to solve through, your regular way, the exact same way I showed you here up in the real part. All right, so now we can talk about instantaneous power, but what if we're not given those, those regular equations? What if we're given some other stuff that's different? Some other equations you might see from, circuits and systems, or the end of circuits 2, you might be given these larger equations, and these you don't see as often, so I'm not really going to go through them very in depth. Another equation for instantaneous power, I don't think I've ever used this in an exam or like practice, but they have it in the notes, so I'm not going to gloss over it. I'm just going to kind of gloss over it, really. IS over VS, or IS times VS over 2, and these are not RMS. These are your amplitudes, so remember how we put AM or VM? That's what those are. So those are your amplitude values. I think they put S for source, but that's what happens. Then you do cosine of, again, the angle between them, theta V minus theta I, and I'm actually going to do phi I because I did the same thing earlier. Minus cosine of 2 omega t minus theta V minus phi I. Now you see how there's a little bit extra stuff here with this minus cosine of this 2 omega t. This is another extra part. I'm not going to get into it. But I guess where this part comes from is it's the same thing as IRMS times VRMS, because ARMS is equal to AM divided by the square root of 2. So that means IM divided by square root of 2 times VM over square root of 2 is equal to IM times Vm divided by the square root of 2 times the square root of 2 is 2. So that's where they get this front part. This back part isn't very important. It's a lot of trig identities we're not going to get into. All right, so that's another way you can solve for instantaneous power if you're asked for it. Another way you can solve for average power is this way, and it's the exact same way, that I showed before, or not really that I showed before, but a different way. You don't have to take the integral of instantaneous power. You can do ISVS again. Those are your amplitudes divided by 2 times the cosine of the angle between them. And what do we notice about this? This is the same thing as IRMS times VRMS cosine theta. Remember from above, this is just reinforces the idea that average power is this value. All right, so now one of the last things we get into for power is power factor. This is very important in your grid kind of work, or the generation of power in distribution plants or generation plants. Your power factor is going to be equal to cosine of theta. Well, what's theta? Well, theta is equal to theta V, the voltage phase, minus the current phase. Does this look kind of familiar? Well, it should, because you notice how this IRMS times VRMS times cosine theta, where theta is the angle between them, is the same thing. So what can we replace cosine theta with? Well, we can replace it with power factor. So this becomes very important because a lot of the time in these power equations, you can really just input cosine theta with power factor. If they give you power factor and your problem is asking for average power, you don't have to solve for anything. You maybe have to solve for IRMS and VRMS, but power factor, don't get confused, because you might be seeing, oh, cosine theta, what's cosine theta? But we have that, it's power factor. Okay, so moving on from that, we can then also say power factor is equal to real power, or your average power. Remember, real power is average power, divided by the apparent power, S. Now, why can we do that? Well, remember from up here, P equals S cosine theta. Remember, cosine theta is power factor. So if we solve for power factor, average power over apparent power. What about for the reactive power? Well, it's not called power factor. I forget exactly what it's called, but this is called something else. I think it's reactive factor. I'm not sure. They told us about this in circuits and systems, but it's kind of getting away from my head. Anyways, that's another way you can solve for power factor. Now, that's going to be pretty much everything for power computations. I guess we could also talk about, there's one last thing called the crest factor. And this can be mostly seen whenever you draw a figure or a waveform. So if you have some sort of sinusoidal waveform here again, we have our Vm, our amplitude, right? It hits that, it keeps going. And then we have our RMS. Right? I guess I can draw a straight line through. Close enough. So what the crest factor is, whatever type of waveform you have, it's going to be equal to the Vm, or your peak, divided by the RMS value. So what if you have something that is much steeper, has a higher amplitude, but has a small period? Something like this. What if we have something like this? Just thinking about crest factor. Well, what do we know? That means if we have our Vm here, our RMS actually is going to be much lower. Our RMS is going to be somewhere here. Think about crest factor as, of course, the ratio between the magnitude or the max divided by the RMS. And so if we have a larger discrepancy between magnitude or the amplitude and RMS, we're going to have a much larger crest factor. So we'll call this 1, we'll call this 2. Crest factor, which we'll denote by CF, CF1 is much less than CF2 because the discrepancy, the distance between VM and VRMS are much, much smaller in waveform 1 as compared to waveform 2. So that's the last thing we have. That one isn't seen as often, mostly because it's more of a visual kind of thing. We don't really have to solve for that value all that often. But that is really all power computations gets into. I believe that's all. Let me make sure. Okay, so we get into inductor and capacitors, but you should be able to derive this given this basic introduction of power computations. Now, I'll probably do another video talking over the significance of capacitor loads and inductor loads in steady state operations. But that part should become a sort of like learning section for y'all. So hopefully y'all can take this, take it from what you will, and solve the practice problems at the end of the textbook or in your notes or in homework especially, and make sure to implicate or apply this sort of basic learning. So hopefully this was helpful. Hopefully this kind of refreshed some ideas. Remember, this isn't only going to be for power electronics, but for any power concentration class you're going to have, as well as the FE exam. You guys need to make sure you have this kind of basic power equations and understanding. All right, but hopefully this helped for y'all. This is just the very introduction. We're going to get into problems later. If you have any problems you want me to solve in specific, send it to me and I'll be able to solve them and help y'all out with that. Anyways, thank y'all for joining.